Okay, so good evening and welcome back to the weekly live sessions on mechanics and control of robotic manipulators. I am Isaac John. I will be handling, yes, good evening. So I'll be handling the weekly sessions on mechanics and control of robotic manipulators. So until now, we have been dealing with the kinematics part of mechanics. We have been dealing with the fundamentals of kinematics, how to do the forward kinematics, inverse kinematics. In the previous week, we have also seen some examples, of robotic manipulators, typical 2D of robotic manipulators, and how to solve the inverse kinematic problem analytically. So this week, it's more or less like an extension of what we have covered in the previous week. As for this week, we'll be covering the topics regarding what we call as differential kinematics. We'll also see something regarding a concept called singularities and why it has to be studied in case of a robotic manipulators. How singularities are relevant. We'll talk about various kinds of workspaces, that is relevant for robotic manipulators. And then we'll also, visit topics, regarding velocities, singularities, and, static force analysis. So just like in the previous weeks, for the first part of this session, we'll go through the summary of all the topics that we have seen, during week 4 lectures. And for the remaining part of this session, we'll solve some sample problems or some sample questions. So regarding week 4, we were introduced to differential kinematics by Professor Shantakumar. We have actually seen how to propagate velocities from the robot's base all the way to the end effector. He has also shown some implementations of velocity propagation using MATLAB. The way these algorithms are formulated uh, are in a recursive manner. So if your robot has multiple links, using the recursive velocity propagation, it's fairly easy and straightforward to propagate velocities from all the joints, starting from the base all the way to the end effector. Then we have also seen the propagation of forces and moments when the robot is in a static equilibrium position. And at the tail end of this week 4 content, we have also seen how to derive the dynamic model of robotic manipulators or equations of motion using Lagrange-Euler method. And we have also seen how to derive the same using something called Newton-Euler method. For the topics 5 and 6, we'll reserve it for the next week. For the current week, we'll only be discussing topics up to topics from point 1 to point 4. All about velocity propagation, manipulator workspace, and manipulator singularities. So if there are any doubts, or if I'm not clear in some of my definitions, or if I'm not clear in any sort of explanations, feel free to interrupt me at any point of time. You can use your microphone or come to the chat boxes. Either ways, it's fine. All right, so we'll basically have an overview of what differential kinematics is. So we have already seen what for a forward kinematic model is. It's basically a mapping between or a mapping from the joint space variable to the task space variable. So in very simple terms, if you have a robotic manipulator with two links connected by two joints, right? If I consider this to be the first joint, I'll call this as R1, denoting a revolute joint. I'll call this R2. And if these are two links, link 1 and link 2, you basically define the configuration of a robot using two joint variables. So I can denote it using two angular coordinates, maybe this being theta1 and this being theta2. And maybe at the end of the robot's arm, you have the end effector. Could be a gripper or could be a welding gun, uh, any sort of end effector. And you define the position of the end effector or the tooltip using the Cartesian coordinates x comma y, right? And we basically denote this vector x comma y using the symbol mu, and we call the vector of Cartesian space or Cartesian coordinates as the task space variables. And the variable that directly correspond to the input into the motors. For example, if you consider this robot to be of 2 degrees of freedom, you will be attaching a motor directly to the joints, and the input to these motors, which correspond directly to the joint variables theta1 and theta2, we call this vector as the joint space variables. And in the like as we have discussed in the previous weeks, if the joint space variables are given, finding out the task space variables is the problem of forward kinematics. Whereas if the task space variables are given, finding out the joint space variables is the inverse kinematics problem. So essentially, the mapping between task space and joint space, you perform this mapping using this forward kinematic model, which essentially says mu is actually a function of the joint variables q, right? So if you differentiate this equation, right, you will end up with an equation which can be represented as a matrix and vector form. So if you take the derivative of mu with respect to time, you will get mu dot. And for any function, arbitrary function, if you take the derivative of the function with respect to the time, you will end up with a matrix. We call it as a Jacobian matrix, where this Jacobian matrix is nothing but is made by assembling the partial derivative of mu with respect to the partial derivative of q. For example, a very brief example, if you have the forward kinematic model of an RR robot, something like the position x has L1 cos theta1 and L2 cos theta1 plus theta2, and y to be L1 sine theta1 plus L2 sine theta1 plus theta2, where we consider this direction to be the x-axis and this direction to be the y-axis. So for any location of the end effector, any location of the end effector expressed in x and y coordinates, we can define any position using this forward kinematic mapping, right? X is L1 cos theta1 plus L2 cos theta1 plus theta2, and y would be L1 sine theta1 plus L1 sine theta1 plus theta2. And if you take the derivative of x and y with respect to time, you'll end up with this following two equations. X dot would be minus L1 sine theta1, then theta1 dot, plus L2, sorry, it'll be minus sine theta1 plus theta2, there is also an L2, then theta1 dot plus theta2 dot. Then for y dot, you will have L1 cos theta1, then theta1 dot plus L2 cos theta1 plus theta2, theta1 dot plus theta2 dot, right? And you can represent this using a vector matrix notation, where x dot, y dot, you can, combine all these together as a vector mu dot. And then you will have a matrix over here. And on the other end, you will have this theta1 dot, theta2 dot. And the components of this matrix would be dou x by dou theta1, dou x by dou theta2. Then for the second row, it will be dou y by dou theta1, dou y by dou theta2. Right? I hope this essentially makes, or this basically makes sense. Right? For example, if you want to expand the first row, x dot would be dou x by dou theta1 multiplied by theta1 dot is essentially dou theta1 by dou t plus dou x by dou theta2 multiplied by dou theta2 by. This is essentially a chain rule, right? Chain rule of x dou. And we take this partial derivative of theta1 with respect to time and partial derivative of theta2 with respect to time as a vector, theta1 dot and theta2 dot. And the remaining partial derivatives, we group it as a matrix, something like this. Right? So if you do that for all the task space variables and joint space variables, you will end up with a Jacobian matrix J. So, as you can see further down this session, we'll be using this Jacobian matrix for a lot of different purposes, to assess the quality of the workspace of the robot, to map, the velocities from joint space to task space. And also, we would also be using the Jacobian matrix to map the forces acting on the end effector to the forces or torques acting on the joints. Right? But in principle, this is how we assemble the Jacobian matrix. So we call this expression as the forward differential kinematic model, where if you know the velocities in joint space, theta1 dot and theta2 dot, and if you multiply the velocities in joint space using this Jacobian matrix, you will get the velocities in the task space. This is about the forward differential kinematic model. It's very similar to the forward kinematics or the forward geometric model that we have seen in the previous weeks. Whereas the inverse differential kinematics model, you will be given a desired velocity of the end effector in task space coordinates, right? Maybe, for example, at any instance, you want your robotic arm to move with a specific velocity along x and y directions. Then what should be the velocity of the joints, individual joints? So that problem is what inverse differential kinematics tries to solve. And you can do so by inverting the Jacobian matrix and multiplying it with the velocities in the task space. Right? And for this Jacobian matrix to be invertible, basically it has to be invertible. First we have to verify whether the Jacobian matrix is invertible or not, because there are some cases where the Jacobian matrix cannot be, inverted. Yeah, so it's very analogous to the forward kinematics and inverse kinematics. In case of forward differential model, you will be asked to find out the task space velocity provided the velocities of each of the individual joints. Whereas in case of inverse differential kinematics, you will be given the task space velocities, maybe a desired task space velocities. You will be asked to find out what should be the input velocities you should be supplying into the motors. That problem you can solve by using this equation. And yeah, so we have seen cases when the Jacobian matrix is square. For example, if you have a robotic manipulator like this, with the 2 links and 2 degrees of freedom, maybe I'll call the first angle to be theta1 and the second angle to be theta2. And suppose you wish to control 3 coordinates or 3 variables in joint space, be it x, y, and theta, right? So apart from the usual Cartesian positions x and y, you also wish to control the orientation theta of the end-effector. But then it's still an RR manipulator. You still only have two joint variables, theta 1 and theta 2. But then how would the kinematic equation would look like? Or how would the forward differential kinematic equation look like? It would look something like this. Mu dot would be J of Q multiplied by Q dot, where Q dot is, the differential velocities in joint space, which is nothing but, theta, theta 1 dot and theta 2 dot for this RR robot. Whereas mu dot in this case would be x dot, y dot, and theta dot. You are trying to achieve a desired velocities in x direction, y direction, as well as theta direction. Right? So this would become a 3 by 1 matrix. On the right hand side, the vector of joint space variables is basically a 2 cross 1 matrix. And the Jacobian in this case would become a 3 cross 2 matrix. Right? You essentially have a matrix that is dot. It's not a square matrix. It has more number of rows than more number of columns. So that essentially means you have three equations, but you only have two unknowns, right? So typically such systems which has more number of equations than unknowns, they are called overspecified systems. And if the three equations are independent, you may not be able to solve the system of equations. There may not even be a unique or an exact solution for such systems. So in that case, you will not be able to find out an equation for mu dot equal to j of q dot. So if you are given a desired task space coordinates, you may not be able to find out the correct or the control velocities q dot, so that the left hand side and right hand side can be equal, right? Finding a q dot such that this equation is satisfied will not always be possible because the system is overspecified, and an exact solution does not exist for an overspecified system. So as a compromise, what we can do is we can try to minimize the error between the left hand side and the right hand side, right? So the objective now would become to find a control input q dot, right, theta 1 dot and theta 2 dot, such that the error between the left hand side mu dot and the term j of q multiplied by q dot is minimized. So we do so by basically a least square optimization problem, where you are trying to minimize the square distance between the left hand side and right hand side. So you can formulate this object optimization by defining an objective, something like this. This is basically mu dot minus j of q into q dot, and this notation basically denotes the norm. And if you take the norm, it's basically the norm square, nothing but the distance square, and an equivalent of distance square. So equivalently, you can also use this notation, because if you have a vector, probably, basically, if you have two vectors A and D, the distance between these two vectors can be written as vector A minus vector D, the whole square, right? Or in another sense, instead of squaring two vectors, you can also take the transpose between the two distances and then multiply. A dot product is also would also be fine. Equivalently, you can take the transpose of the vector that you want to multiply or you want to minimize, and then multiply it with the same vector, A transpose A. It's still equivalent. So, and again, minimizing the distance would also be equivalent to minimizing the square of the distance as well. So now you have essentially declared an objective function. We denote it as L, which is basically a scalar. It's not a vector anymore. It's a scalar because it's a distance. We are trying to minimize the distance between mu dot and J of Q multiplied by Q dot. Now, just for clarity, let's see what these dimensions are. Right. So in this case, mu dot is a vector 3 cross 1. And J of Q earlier we have established this to be 3 cross 2 and Q dot is 2 cross 1. So this entire term is basically a 3 cross 1 vector. And if you take the transpose of it, it becomes a 1 cross 3 vector. So I'll write the dimension here as 1 cross 3 for this entire term. And for this term, the dimension would be 3 cross 1. And combine it, you will get a 1 cross 1, which is nothing but a scalar. Right? So the dimension of your objective function is 1 cross 1, which is essentially a scalar. So now what your objective is, you have to find out a Q dot, right? You have to find out a Q dot or the control input such that the objective function is minimized, right? So to find out a control input Q dot so that the objective function is minimized, you have to take the derivative of this objective function with respect to the control input and equate it to 0. So whatever Q dot that satisfies this equation would correspond to its minima, right? So essentially, you are taking the derivative of a scalar with respect to a vector. So the expected dimension of this would be, because Q dot is essentially a vector. So this expression would give you a vector of 2 quantities. So if you have this term, if you have your objective function defined as such, taking the derivative of this objective function would, give you this expression, right? It's nothing complicated because if you take the derivative of x square with respect to x, you will get 2x, right? Or similar to if you take a function x minus a, the whole square, and if you take the partial derivative of the function with respect to x, you will get something like 2 multiplied by x minus a. Similar analogy is what we are using here, right? You have a square of a function, and if you take the derivative of this function, you will get you will get 2 multiplied by the function mu dot minus j of q multiplied by q dot. Then you also have a coefficient, of q dot that will come out here, right? So there should be a 2 here, but since there is an equal to 0 on the other side, you can ignore or you can omit the 2, or you can even ignore this minus sign as well, right? So essentially, the derivative of this expression is nothing but this as per equation 2. Now, if you rearrange this expression, mu dot multiplied by j of q multiplied by q dot transpose j of q, if you expand it and if you take this portion to the other side of the equality, you will get this equation, right? Equation number 3, right? And now from equation number 3, if you take the transpose on both sides, take the transpose of this side, you will get this term, right? Because AB, the whole transpose, is nothing but B transpose A transpose. right? So in that regard, if you take the transpose of this entire term, you will get JQ transpose mu dot transpose the whole transpose. That makes it mu dot. And if you take the transpose of this side, you will get JQ transpose J of Q multiplied by Q dot. That is what I have written here, right? So now your objective is to find out Q dot. So if you take this entire term and bring it over to your left-hand side, what you are essentially doing is you are taking this entire term and multiplying both sides of this equation with its inverse, right? So if you do that, you will end up with this equation, right? This is what your Q dot would give you. Yes. Any doubts? Hello. If there are any doubts, let me know. Otherwise, I'll continue. Okay, I thought I was someone was asking a doubt. All right. So now, if you take these two terms to the other side, you will end up with an expression for Q, which is nothing but this big lengthy expression multiplied by mu dot. So I'll write it in a simplified manner. Q dot is probably a J. Maybe I'll have a symbol here plus mu dot, where this J plus or J cross is nothing but J of Q uh, transpose J of Q, the whole inverse multiplied by J of Q transpose. So we call this entire term as the left pseudo inverse. Left pseudo inverse of the rectangular matrix J of Q. Right? If the Jacobian matrix were square, you only need to take a regular inverse. Instead of the pseudo inverse, Q dot would have been J inverse mu dot. But since we have a rectangular matrix, that too, a long matrix, which has more number of rows than columns, we take something called a left pseudo inverse, and the expression for this left pseudo inverse is derived as so, right? And what it basically gives you is it gives you an approximate solution Q dot that minimizes the least square error between mu dot and J of Q multiplied by Q dot. Right? It's not an exact solution. It's an approximate solution that minimizes the error between mu dot and J of Q multiplied by Q dot. All right. And for this pseudo inverse to exist, this inverse have to be in existence. And for this inverse to exist, J of Q transpose J of Q, the whole inverse, for it to exist, it should be, you know the formula, right? Adjoint of J of Q transpose J of Q divided by the determinant of J of Q transpose J of Q. So for this inverse to exist, the determinant of J of Q transpose J of Q must be non-zero. Then only this term will exist. Then only the pseudo inverse will also exist. Pseudo inverse is actually this entire, right? In specifically, we call it as a left pseudo inverse, and that is only valid when your square matrix has more number of your Jacobian matrix has more number of rows than the number of columns. That is a case you will encounter when the system is overspecified. Right? You're trying to control more number of variables with minimal or fewer number of joint variables. That is one example. Right? And the solution is also an approximate solution. So what happens for the other case? When there are in this case there were more equations than unknowns, and in the other case we have more unknowns than equations. So one example I can give you is that you can instead of a 2-hour robot you can have a 3-hour robot with 3 links connected by 3 revolute joints, and each of these revolute joints are actuated by a coaxial motor. And I can specify the joint variables of each of these joints as theta1, theta2, and theta3. And now I'm trying to control the task space x and y, just the 2 task space, but with 3 motors. So how would your forward differential kinematic equations would look like? It would look something like x, y would be a Jacobian matrix, sorry, x dot, y dot would be a Jacobian matrix Q multiplied by theta1 dot, theta2 dot, and theta3 dot. So your mu side, the vector mu or the task space vector is now 2 cross 1, and your joint space vector is 3 cross 1. But and in that case, your Jacobian would become 2 cross 3. Right now, the Jacobian matrix is short and broad. It's more wider than the previous case. So as you can see here, the number of equations is only 2. There are only 2 equations, but the number of unknowns are actually 3: theta1 dot, theta2 dot, theta3 dot. So the goal now here is, you are given a desired velocities in task space, x dot and y dot. You want your end effector to move with a desired velocity in x dot and y dot direction. What should be the input, that you have to give into the motors? The inputs theta1 dot, theta2 dot, theta3 dot. Right? So typically you have this system of equations. Mu dot is j of q multiplied by q dot, and q dot would be j of q inverse mu dot. So typically, if j of q were square, you could have simply inverted the Jacobian matrix and pre-multiplied it with the desired velocities. But now, since our matrix is now, a broader matrix, a broader rectangular matrix, we cannot take a normal inverse, something like this. So what can we do? Now, let's see what type of system that we are dealing with. So this system is basically underspecified. When the number of equations is fewer than the number of unknowns, right? The system is basically underspecified. So as a result, it can have multiple solutions, right? Maybe, if the robot has to reach a particular XY position, it can reach in, this configuration. It can reach in some different configuration like this. It can reach, in another configuration. Similarly, there could be multiple possible ways that through which it can achieve or it can reach this position. One another example is, if you consider intersection of 2 planes, right? For defining a plane in 3D, you require 3 variables, right? X, Y, Z. So if you want to consider intersection of 2 planes, you have basically 2 equations, but then the number of variables are 3, X, Y, and Z. And as you know, 2 planes intersect along a line. So there are infinite possible points, infinite possible X, Y, Z coordinates, which would corresponds to the line where the 2 planes intersect. So, when the system, in essence, when the system of equations is when the number of equation is less than the number of unknowns, it can have multiple solutions. And in a lot of cases, it can have infinite number of solutions. Just like, when two planes intersect, there are infinite points lying along a line where these two planes intersect, right? So typically, out of all these infinite solutions, we would take a solution corresponding to the minimum norm, the solution that has the minimum norm. So our objective is to find out this theta 1 dot, theta 2 dot, theta 3 dot, such that mu dot is equal to a Jacobian times q dot. If a desired task space velocity is q1, find out, you have to find out this q dot for any desired mu dot. So essentially this minimum norm solution corresponds to a solution where the norm of q dot is minimum, right? Where if you have a vector q, norm of q is defined as q1 dot square plus q2 dot square plus q3 dot square. Everything comes under a rule. So where this q vector is defined as q1, q2, q3, right? So you would select a solution. Out of all the possible solutions, you would select a solution which has the minimum norm. It would also you would also get an equivalent effect if you take the square of the minimum norm, right? So in that case, you don't even have to consider this square root, because you are taking the square of the norm. We do so in robotic manipulators. The reason why we are doing this in robotic manipulators is that the kinetic energy or the energy spent is actually proportional to the square of the velocities, right? Half mv square, and the energy spent is actually proportional to the square of the velocities of the joint variables. So minimum norm solution corresponds to the solution that spends or that requires the minimal energy, right? Out of all the solution corresponding to minimal energy, corresponds to this minimum norm solution. So that is why we are actually, going with this minimum norm solution out of all possible, of all possible solutions. Now, let's see how to derive or how to obtain this minimum norm solution from the data that we have. So we define the minimum norm. If you have a vector q dot transpose q dot is basically the square of its norm, right? If you have a vector q1, q2, q3, then q dot transpose q is nothing but q1, q2, q3 multiplied by q1, q2, q3. So if you do this matrix multiplication or this vector multiplication, you will end up with q1 square plus q2 square plus q3 square, right? This is what we want to minimize. This is your objective that you want to minimize. So the first part of your objective function, right, is corresponds to the minimum norm of this vector q. And the second part of your, objective function is basically what we call as this constraints, right? So this becomes like a constraint optimization problem. So, this first term alone does not mean anything, right? It can be any, it can be 0, 0, 0, which corresponds to a minimum norm. But then we cannot select any arbitrary or any random q dot. The q dot that has the minimum norm should also follow this constraint, right? Mu dot minus j of q dot. The constraint, it has to follow this constraint. This should be equal to 0, right? Or we have to also minimize the gap between mu dot and j of q multiplied by q dot. So that becomes a constraint, and we, give individual weights to each of these constraints. Maybe a constraint in one direction could be more uh, valuable than the constraint along other direction. So we multiply these constraints with weights. We call this as a lambda. In optimization terms, we call this lambda as something called a Lagrange multipliers. This is something we usually encounter in constraint optimization. All right. So now our objective is to find out a minimum norm solution such that these constraints are also satisfied. So now, we have to optimize this objective function in terms of q dot, because ultimately that is what we are trying to find out, q dot, and also this weights. These weights are also essentially unknown. So you have to optimize q dot, or you have to minimize this objective function with respect to q dot and this vector lambda. So we do so by taking the partial derivative of this objective function with respect to q dot and lambda. So if you do the first case, if you take the partial derivative of objective this Lagrange multiplier with respect to q dot, you will end up with this equation, right? Because this is something like x squared. So if you take the derivative of x squared with respect to x, you will end up with 2x. So here you will end up with 2q dot. And if you take the derivative of this term with respect to q dot, you will end up with minus lambda transpose j of q, right? Because the coefficient of q dot is lambda transpose j of q. So that's what you end up here. Similarly, if you take, the partial derivative of the Lagrange, the objective function with respect to lambda, you will end up with this equation, which is nothing but the constraints themselves, right? This term would turn out to be 0 because, there is no term that involves lambda. And for the second term, the coefficient of lambda is this term. So if you take the partial derivative of this term with respect to lambda, you will only end up with this term. So that's what we have written over here. And now from equation 7a, you will get an expression for q dot from equation 7a, right? So I'll equation 7a, I'll just try to reproduce here. So equation 7a is nothing but 2q dot transpose minus lambda transpose j of q. Or if I bring everything to the either sides of the equality, you will get an equation something like this, right? So if you take the transpose on either side of the equality, you will get 2q dot would be j of q transpose lambda, and as a result, q dot would be j of q transpose lambda by 2. This would be your q dot in terms of lambda. Now you substitute this q dot into this equation, right? If you substitute this into equation 7b, you will end up with an expression something like this. Mu dot is j of q transpose lambda by 2, right? So equation 7b is nothing but mu dot I'll write it in this way, mu dot equal to j of q multiplied by q dot. So instead of q dot, I'll substitute this equation, which is nothing but j of q transpose lambda by 2, right? So now what I'm going to do is I'll substitute this equation. I'll substitute this equation back into equation 7a, right? So from this equation, I'll have to rewrite everything in terms of lambda, right? So lambda now becomes 2 mu dot, sorry, it will become 2 mu dot, then j of q transpose the whole inverse. So I'll write it properly. Lambda now becomes 2 multiplied by j of q transpose the whole inverse mu dot. This will become your lambda. And if you substitute this lambda into the first equation, 7a, you'll end up with this big equation, right? And finally, you will end up with an expression for q dot, right? Your q dot would be j of q transpose j of q transpose this entire thing inverse mu dot. So this entire term, this entire term over here, we call this as a right pseudo inverse. Earlier it was a left pseudo inverse. Now we call this as a right pseudo inverse. And this would only exist if this inner inverse would exist. If only this inner inverse would exist. That inner inverse j of q transpose the whole inverse would only exist if j of q multiplied by j of q transpose, the determinant of this term is non-zero. If this is non-zero, right? So this term, we call this term as the right pseudo inverse. So in summary, when we have an overdetermined system, when the number of equations is more than the number of unknowns, we go with the left pseudo inverse. But in the case where the number of equations is less than the number of unknowns, we go with the right pseudo inverse. So this solution, q dot, the solution q dot equal to j pseudo inverse. Maybe I'll write it as right pseudo inverse multiplied by mu dot. This will give you the minimum norm solution, right? If you have a desired mu dot, the solution q dot corresponding to j right pseudo inverse multiplied by mu dot will give you the minimum norm solution, right? Out of all the infinite solutions, you will get the minimum norm solution. So yeah, that's about the forward and inverse differential kinematic mapping. Now we deal with something called the velocity mapping, basically. So in the previous weeks, we have actually seen, how to take the derivative of, how to express vectors in different frames of references. For example, if you have a fixed frame of reference, maybe I'll denote it as A, which is a ground fixed frame of reference. Maybe I'll denote the coordinates as XA, YA, and ZA. And consider we have a rotating frame of reference. I'll name this as frame B. And I'll label the frames as XB, YB, and ZB. and I have a point Q, which is referred with respect to frame B. So I'll label the position vector of point Q referred to B as position vector of Q with respect to B. And I also represent the position of this mobile frame or this rotating frame with respect to the fixed frame using this vector, position vector of B with respect to A. Now, the resultant of these two vectors, that is, position vector of Q with respect to A is nothing but the vector sum of, these two vectors. So that's what I've written over here, position vector of uh, position vector of uh, Q with respect to A would be position vector of B with respect to A plus position vector of uh, you know Q with respect to B. But
Sir,
then,
1 minute, sir.
Yeah.
Sir, Q is a point in B coordinate, no, sir?
Q is a point in B coordinates. Yes, it's
Okay.
represented in B coordinates.
Okay, sorry.
So in
Okay,
that
okay, okay.
case, everything has to be referred with respect to a single frame. So here, like we have represented the previous two vectors in A frame, but B, the vector Q was actually referred with respect to B frame. So, to bring that mapping, we have to pre-multiply that with the rotation matrix of B with respect to A. Now, basically, you know, everything is now referred with respect to a single frame of reference, with respect to the frame of reference A. The reason why we are doing so is, if while we were discussing you know, the DH convention for any rigid body that we have, if you consider this to be the ith rigid body I, maybe you have a joint over here. I'll call this joint I, whose axis is pointing vertically upward like this is an I, so that, this link I can rotate about this vertical axis, maybe theta I. As per the DH convention, we always have a frame of reference attached to the proximal end of a rigid link. What I mean by proximal is, if you have, the ground in this direction, towards the left, and if you have the end effector to the right of the manipulator, the end of the rigid link that is closer to the base, we call it as the proximal end. And the end that is closer to the end effector, we call it as the distal end. Right? So for any rigid body, if a rigid body is floating in space, maybe for the ith rigid body of a manipulator is floating in space, it will always have a frame attached to the rigid body itself. Right? So in that case, any attribute associated with the ith rigid body, maybe the center of gravity, or maybe its angular velocity, its angular acceleration, all these sort of attributes are, are referred initially with respect to the frame of reference that is attached to the body. Right? Otherwise, if you are referring that, it'll be very difficult to straight away define the center of gravity of a floating link with respect to a fixed frame. Maybe if I represent the fixed frame here, fixed frame here, like as frame 0, which is the ground, it's not easy to represent the center of gravity of a floating link with respect to the ground, because it keeps on changing its position and orientation. It's highly dynamic. What we typically do is we represent the attributes of a floating link with respect to a frame, attached to the rigid body. Because if the rigid body is floating, the frame is also floating along with it. The coordinate frame is also floating with it. So with from that local frames perspective, everything is fixed. Nothing changes with time, because as the rigid body moves, the frame also moves with it. So everything is like the moment of inertia, the center of gravity, the link length, everything is constant with respect to the floating frame of reference. So similar analogy can be brought here, right? We have a frame B. Maybe you can consider frame B to be attached to a floating link, a rigid body, and this vector, vector of Q with respect to B, maybe you can consider it to be an attribute of that specific rigid body, maybe center of gravity, center of mass, things like that. So it's always easy to, it's always easy to refer a link's individual attribute with respect to its own local frame of reference. So that's why we are, denoting, we are using this, uh, we are expressing everything with respect to the local frame first. Then using the rotation metrics, we are bringing it back to the, ground frame of reference. All right. So we were discussing the velocity propagation. I think before we get further on to this expression, I'll just talk why we are doing this velocity propagation. So for example, if you have a, robotic manipulator having, multiple rigid bodies, something like this, maybe multiple rigid bodies, and each of these rigid bodies are connected by joints, maybe a revolute joint or spherical joint. And each of these joints are associated with a joint variable, maybe theta 1, theta 2, all the way to theta n. And your end effector will also have a velocity. You can maybe express that in task space coordinates, maybe x dot, y dot, z dot. If the robot is a spatial robot, you will have to express the velocities in linear velocities, x, y, z, and also the angular velocities, theta dot, maybe theta dot, psi dot, phi dot. All six components, six linear components and six rotary components. So the reason why we are doing this velocity propagation is we need to find a mapping between the velocities in joint space, theta 1 and theta 2, theta 3, a mapping from the joint space all the way to the task space. So here you can actually see that each and every joint would contribute to the velocity in task space. For example, in a very simple case, if you have a 2R robot like so, with this being theta 1 and this being theta 2, if you rotate theta 1 alone while keeping theta 2, you will have a corresponding linear velocities x dot and y dot. If you keep theta 1 stationary and keep theta 2, if you rotate theta 2, you will have another set of x dot y dot linear velocities. And if you actuate both theta 1 and theta 2, any linear combination or any sort of combinations would have an effect on the velocities at the end effector, in task space. So the joint propagation model, the purpose of this joint propagation model is you basically start from the base and you will accumulate the effects of all the joint variables. And finally, you will end up with an expression for the velocities in, you will end up with an expression in task space, or basically the velocities of the end effector. So you begin from the base. Obviously, base has a zero velocity, and then you consider the effect of the first joint on the end effector, Then you will consider the effect of first and second joint on the end effector, first, second, third joint on the end effector. So it's like it's propagate the velocities from base all the way to this end effector. That's what we are doing in velocity propagation, right? Propagating the effects of all the joint variables or all the motors to the determining the cumulative effect of all these joints at the end effector. All right. So now that we have established this simple, vector addition, we can obtain the expression for velocities by taking the derivative of, this expression, taking the derivative of uh, this vector equation. So how would you do that? If you take the derivative, I'll write it like this: derivative of position vector of q with respect to a. I'll denote the derivative with the sign dot, would be derivative of position vector of b with respect to a dot. And for the second term, I'll have to apply the chain rule, right? So I'll apply the product rule, ARB multiplied by BPQ dot plus ARB dot multiplied by BPQ. This is what the derivative would look like. So BPQ is basically the rate of change of the vector q with respect to b. And in most of the cases, in terms of a rigid body robot, this vector would always be a constant, right? Because this is always attached to the frame B, and in most of the cases, it's always going to be a constant, the derivative of P. So, in most of the cases, we can disregard this to be 0 wherever applicable. And now we have to know what is the derivative of, what is the derivative of this rotation matrix, derivative of a rotation matrix. So how do you find out the derivative of a rotation matrix? What is the basic property of that? So, that rotation matrix is an orthonormal matrix, right? So R multiplied by its own transpose, R transpose, would be an identity matrix, right? Because R is orthonormal and R transpose is equivalent to its inverse. And in that regard, R transpose is nothing but R inverse, which is nothing but this identity matrix, right? So if I take the derivative of this expression, you will get it as, if I apply the product rule or the chain rule, I'll get it as R dot, R dot R transpose. I'll get it as R dot R transpose plus R dot transpose. This would be 0. So if I bring everything to the other side, maybe I can rewrite this expression like so: R dot R transpose plus R dot R transpose, the whole transpose is 0, right? Because these two equations are equivalent. So what does that mean? So if you consider this R dot R transpose as S, S plus S transpose is 0. So what does that tell you? R dot R transpose is a skew symmetric matrix, right? R dot R transpose is S, which is nothing but a skew symmetric matrix. All right. So now what is R dot? R dot R dot would be S multiplied by R, right? Uh, I think someone's mic is actually on. If you could mute it, it would be nice because some sort of interruptions are coming. Okay, thank you. All right. So if R dot and R transpose is a skew symmetric matrix, I can multiply R dot R transpose with its inverse, maybe which is essentially R because transpose and its inverse is essentially the same thing. And on the right hand side, you will get S multiplied by R. So R transpose R is again an identity matrix. So I'll just remove it away. So the expression for R dot is a skew symmetric matrix multiplied by the rotation matrix itself, right? And typically, this skew symmetric matrix is nothing but, uh, omega. You'll have to take my word for it because, for example, a very brief example, if you consider this rotation matrix as an example, as a pure rotation about, z-axis, maybe cos theta minus sine theta, then you have 0, then sine theta, cos theta, 0, then 0, 0, 1. Now, this is an example of a pure rotation about z-axis. And if you take the derivative of this rotation matrix, r is a dot, this would be minus sine theta, theta dot, and this will be minus cos theta, theta dot, then 0, then cos theta, theta dot, sine theta, theta dot, 0, then 0, 0, 1. And if you take this, if you multiply this throughout, if you multiply the same R dot and R transpose, because this would be your R dot. And if you take the transpose of this rotation matrix and if you multiply this out, you will get a skew symmetric matrix, which is of the form, for any skew symmetric matrix, the diagonal terms are 0. And since this is a pure rotation about z-axis, you will get at something like 0, 0, maybe theta dot. This will be minus theta dot, 0, 0. This is a skew symmetric matrix. So this is with respect to a pure rotation about z-axis. But in general, if it is a general rotation, rotation about x, y, and z-axis, the skew symmetric matrix would look something like this. It would look something like all the diagonal entries would still be 0, 0, 0. Then this term would be omega x. This term would be minus omega y. This term would be omega z. And here you will have minus omega z. Here you will have omega y. Here you have minus omega x. So this would be your skew symmetric matrix. You can verify that with the general rotation matrix and see if you get this term. So so now, as we have proved earlier, R dot would be nothing but this skew symmetric matrix S, which is this thing multiplied by the rotation matrix R. The rotation matrix itself, as we have shown over here, right? So equivalently, you can write this product of the skew symmetric matrix and this matrix multiplication as a cross product also. So in most of the cases, or in all cases, if you have two vectors, A and B, A cross B, typically, how would you do this A cross B? You basically solve this by, if you have ijk and A1, A2, A3, which are the components of A, and B1, B2, B3, which are the components of B, you would take the determinant of this matrix to get the expanded form of A cross B. You can also get the same result, using an equivalent matrix representation, which would look something like, a skew symmetric matrix multiplied by the vector B, right? B1, B2, B3. And this skew symmetric matrix is nothing but, A1 minus A2, A3, then minus A3, A2, minus A1. So you can also represent the cross product using a matrix and a vector representation. So I'll call this skew symmetric matrix as A tilde and this vector to be B, right? So A cross B and the skew symmetric matrix representation of A multiplied B are essentially the same. So in that regard, you can replace this derivative of this R dot with respect to time using this notation, right? R dot derivative of position vector of B with respect to A, you can either write it as a skew symmetric matrix, angular velocity of B with respect to A, multiplied by the rotation matrix B with respect to A, or you can write it as the angular velocity vector cross this term, the rotation matrix of B with respect to A. Either of these terms are essentially equivalent. So I hope we can all agree with this final expression. This is nothing but the derivative of this position vector. And now, when you carry that to the relevant terms that we, to the relevant terms that we actually want, we have to propagate the angular velocities, from the base to the end effector, and then we also have to propagate the linear velocities, from the base to the end effector. So, for example, if you have a link I, something like this, and if you have a link I plus 1, I'll label this as I plus 1. You will have this link here as I, and towards this side you will have the ground, and towards this side you have the end effector. And on the ith link, at the proximal end of the ith link, you have the local frame attached as Zi, and on the proximal end of the I plus 1 frame, you have the frame attached I plus 1. Now, associated to the ith frame, you have the angular velocity of the ith frame as omega I, and angular velocity of frame I plus 1, you will have it as I plus 1, omega I plus 1. Then how would you propagate the angular velocities? It's if you have two vectors, angular velocities, it's nothing but simply you can add the angular velocities, right? Omega I would be omega I plus 1 is nothing but omega I, right? The angular velocity of the I plus 1 frame is, the angular velocity of the ith frame plus, since if it is a revolute joint, it will have its own, rotary angular velocity, right? That's why we have this term corresponds. Plus theta I plus 1 dot. Right? I hope that basically makes some sense, because angular velocity of the current joint would be angular velocity of the previous joint plus the angular velocity contributed by the rotary motion of this link. Because if you consider this link to be connected to the previous link using a revolute joint, if this is a revolute joint, it will have an angular velocity about its own axis, which is theta I plus 1 dot. Right? So the terms that is contributing to omega I plus 1, would be the previous omega I plus the angular velocity of the current frame. But now, we haven't basically defined, we haven't defined it with respect to what reference frame. Like we have only added the vectors, but everything will have to be referred with respect to a single frame of reference, right? And for our convenience, we prefer everything to be referred with respect to its own frame of reference. So if you want to find out I plus 1, if you want to find out the I plus 1 angular velocity, it has to be referred with respect to its own frame of reference, I plus 1. And omega I of the previous link would be referred with respect to, the ith frame. So to bring it forward to I plus 1th frame, we have to multiply it with the rotation matrix I plus 1 with respect to I. And, this one, theta I plus 1, this is always associated with, the frame of reference Z I plus 1, right? And as per the DH convention, we know that Z I plus 1 is always along the axis of the joint. If it is a revolute joint, Z I plus 1 is always along the axis of the revolute joint. And as a result, this vector theta I plus 1 will only have one component, that is the Z component, 0, 0, theta I plus 1 dot. Right? So this is how you propagate angular velocities starting from the 0th link all the way to the final link. Right? For the very first link, this term would be 0, right? Because this term would correspond to the ground's angular velocity, that is 0. So the angular velocity of the first link would only correspond to this one. And as you propagate, this term will also, become more and more active. So this is how you propagate, the angular velocities. And this equation is only valid when the current joint or the I plus 1 joint is a rotary joint. If the I plus 1 joint is not a rotary joint, if it is a prismatic joint, we won't be having this term, right? Because the joint will not be rotating, it will be translating. And it does not, it really won't contribute to the angular velocity. Instead of rotation, it will only translate. And, the angular velocity of the current joint would be same as that of the angular velocity of the previous joint, because it's in case of a prismatic joint. All right, so that's how we propagate angular velocities. And in a similar manner, we propagate basically the linear velocities. Maybe if you can recall how we derive the general vector equation, maybe you can recall this expression. We have this term. We have a term where we have this omega cross some term. Right? For example, if you have a link like this, ith link, and you have an I plus 1th link. This is link I, this is link I plus 1. You have Zi attached to the ith link and Zi plus 1 attached to the I plus 1th link. And for the time being, you can consider all of these joints to be revolute joints, rotating about a vertical axis. So if you know the velocity of the ith link, Vi, if that is already known, what would be the velocity of this frame, I plus 1? So Vi plus 1 would be nothing but Vi, the velocity of the previous joint, plus omega cross r, something equivalent to omega cross r, because omega cross r is also a linear velocity. And omega would be the angular velocity of this joint. We represent it as omega I cross r would be the distance between, these two links. Maybe I'll represent this as position vector of I plus 1 with respect to I. Omega I cross position vector of I plus 1 with respect to I. This is how you propagate velocities. But, same as in the previous case, if you want this to be implemented in a recursive manner, everything will have to be represented with respect to a single frame of reference. Everything will have to be referred with respect to the frame of reference of I plus 1. And since this is recursive, the velocity of the previous frame is already expressed in ith frame of reference. And angular velocity will also be referred with respect to ith frame of reference. And if you want everything to be referred with respect to the I plus 1 frame of reference, you have to multiply this entire equation by the appropriate rotation matrix. So if you multiply the left-hand side and right-hand side with R I plus 1 with respect to I, if you multiply this entire equation with respect to this rotation matrix, you will end up with this equation, right? I plus 1 multiplied by Vi plus 1 would give you the velocity of I plus 1 frame with respect to I plus 1, right? Velocity of I plus 1 with respect to I plus 1 itself. And if you multiply this entire right-hand side with respect to, this rotation matrix, you will end up with this entire expression. Okay, however, if the joint is not a revolute joint, if it is a prismatic joint, instead of rotating about this axis, it will translate about this vertical axis up and down. So in that regard, you will also have one more component like this. Apart from this, you will have one more component that will accommodate this translatory motion as well. So for prismatic joint, the recursive velocity propagation equation would be something like this. You have the velocity of the previous joint. You have, the centrifugal component, omega cross r, and then you also have this, slip or the linear component, the sliding component as well. That is for prismatic joint, right? So you begin the velocity propagation all the way from the first link, to the final end effector position. All right. So that's about velocity propagation. So a similar analogy can be brought to static conditions actually, right? So for example, if you consider a link, as I've said before, a link has two ends. One is called the proximal end, and you have a distal end. And if you consider the entire robot manipulator, it will be consisting of a series of rigid bodies. And in statics, what we do is instead of propagating the velocities, we propagate the forces, right? And this time, instead of propagating it from base to the end effector, we would be propagating from the opposite direction, from the end effector to the base. So like, for example, if you consider this tip to be the end effector, and if the end effector is subjected to some forces and moments, maybe, in 3 dimensions, you will be subjected to F1, F2, F3, the force vector, and you will also be subjected to some moments, M1, M2, M3. If the end effector is subjected to some forces and moments, what should be the forces and or moments that each of these joints have to exert such that the robot will be in static equilibrium? It won't collapse. So we are trying to solve that problem using robot statics, right? For a robot to be in static equilibrium at any working operation, what should be the forces exerted uh, by the joints? So again, very similar to the velocity propagation, we also do the force propagation, but this time it will be in the backward direction. So if you consider this to be a link, maybe if you consider this to be the ith link, you will have a frame here. We call this the frame Isra. If this is the Isra axis, this is the frame corresponding to the ith link. And if you have an I+1 link, you will have a frame over here, Zi+1, right? And the forces acting on this link are expressed in ith frame as well as I+1 frame. So you will have, Fi+1 vector, and you will have Ni+1 vector. And on the proximal end, you will have this Fi vector and this Ni vector. And the distance between the two frames is essentially the link length of the mechanism. So here, maybe I can represent this length between these two frames as position vector of I+1 with respect to I. Now for force propagation, all you have to do is, you do the force balance, you take the force equilibrium. So, forces on the proximal end is nothing but the forces on the distal end. Easy as that. Or, the net force is 0 for static equilibrium. And you also do the moment balance, right? Net moment on the ith frame of reference is nothing but the moment at the distal end plus the moment contributed by the force, right? This is R cross F. This distance multiplied by Fi+1. So this is nothing but a simple force balance and a moment balance. So, it will propagate all the way from end effector all the way to the, to the ground. So the force propagation model is given by this equation, right? It's just a force balance, and the moment propagation equation is given by this equation. Again, moment balance. Or in other ways, net force acting on a link is 0, net moment acting on a link is still 0. All right. So we have talked about the static forces, the static equilibrium problem. Typically, the challenge is to find out, or maybe in this case, if you consider all the joints, if you consider the joint variables in the wrench acting on the joint variables, represent the wrench acting on the joint variables using the simple tau, and the wrench acting on the end effector as F, you can still use the Jacobian matrix to have a mapping between the wrench on the joints and the wrench on the task. It is done so by using the Jacobian matrix J transpose F. This is how you do the force mapping. You can do so by a simple conservation of power, where this tau is, the torque on joints. This is nothing but the velocity, joint velocities. And this is the wrench, the forces or moments or combination of both on task space. And this is the task space velocities. And a wrench multiplied by its corresponding velocity is nothing but the power. right? So power is always conserved. It's still the same. If you compute the power in joint space, or if you compute the power in task space, it's conserved. It's still the same, right? So considering the conservation of power, tau dot product with q is nothing but f dot product with mu dot. If you rewrite it using the inner product convention, tau transpose q dot would be nothing but f transpose mu dot. And this mu dot from kinematics. Mu dot is nothing but j of q multiplied by q dot. And if I substitute this equation in place of q dot, you will end up with this equation, right? So this q dot and q dot will get cancelled. And finally, if you take the transpose of both left-hand side and right-hand side, you'll end up with this equation. Tau would be j of q transpose f. So if you know the loads the end effector is subjected to in terms of f, you can compute the torque that is required so that the robot can hold its location while being in static equilibrium. Or if you know the torque that you can supply to the motor, you can also using this forward relation, you can also know how much force that end effector can basically support. Either ways, you can have this forward static problem or inverse static problem, similar to the forward or inverse kinematics. Right. Now we talk about singularities. In singular configuration, the number of degrees of freedom of end effector is inferior to the dimension which generally operates. Right. So in some cases, if you have a 3 degrees of freedom robot, sometimes in some configuration, there will be a degeneracy in degrees of freedom. Right. It becomes a 2 degrees of freedom robot in some extreme cases. So one such case is when two axes of prismatic joint becomes parallel and two axes of revolute joint becomes identical. So one example is, if you have a robot with two prismatic joints, maybe this is one link that can slide back and forth. And you have, another link that can slide back and forth in this direction. So the tip of this robot will have, it can go vertically up and down, and it can also go side to side. So the workspace would be, a rectangular XY space. This tip can achieve, any space in X and Y coordinates. But then suppose that these two joints are not adjacent. There are several joints in between these two prismatic joints, right? And maybe in some configuration, these two prismatic joints aligns, maybe vertically up. Maybe in some instance, these two prismatic joints, maybe there are several joints here, and second prismatic joint will also align like this. So irrespective of if you actuate the first prismatic joint or the second prismatic joint, irrespective of what you do, you will still get the same degrees of freedom, right? Instead of two independent motion, if you move the first prismatic joint, you will get the vertical up and down motion. If you move the second prismatic joint, you will still get the vertical up and down motion. So irrespective of what joint you move, you will still get the same motion. So you have essentially lost the degrees of freedom from 2 to 1. So such kind of cases happen when two prismatic joints become parallel or two revolute joints, when the two axes of revolute joints coincide, right? So instead of two independent motion, you will only get one independent motion. So such cases where it loses the degrees of freedom is what we call as singular configurations. And at singular positions, the end effector loses one or more degrees of freedom as the kinematic equations become linearly dependent, right? And singular configurations may be avoided as velocities required to move the end effector becomes theoretically infinite. So one example I can tell you is, if you have this classical 2R robot, RR robot, something like this. So maybe you can consider this to be an arbitrary position, right? I'll denote this as x-axis and y-axis. Suppose if the RR robot is fully stretched, maybe along the x-axis, something like this. If this is x-axis and if this is y-axis, what will happen if I try to exert a force in this direction? No matter how hard I try to push along this axis, it won't move. It cannot move along x-axis, right? Or, if I want to have a velocity along x-axis, when the robot is fully stretched, when this arm is fully stretched, it can only have a velocity in this direction, right? Along y direction. No matter how hard I try, I cannot have a velocity component along x direction, right? Because it's already fully stretched. It cannot move in x direction any further. But in any arbitrary position, something like this, I can have two components of velocity, one maybe like this or one maybe like this. So you can have velocities in any direction as a linear combination of two velocities, two independent velocities. But in this case, you cannot have a velocity along x direction, right? Because it's fully stretched. It cannot stretch any further. So that is a fully it's a singular configuration, right? Because even if you apply some theoretically it becomes velocity is required to move and effector becomes theoretically infinite, right? So even if you apply infinite velocities to the joint variables, it does not make any sense, right? No matter how hard you try or how high of a velocity you apply to the joints, you still cannot get a velocity in this x direction because it's fully stretched. So such configurations are called singular configurations. And the same is also true when the arm is extended in this manner, right? Fully stretched. Both of these links are aligned along a straight line. So the robot cannot achieve a velocity along this direction. It can only achieve a velocity in this direction. It cannot achieve a velocity in this direction, along the length of the link. That is also a singular configuration. So similarly, for a 2R robot, any fully extended or fully folded, maybe if this is the first joint, second joint can be fully folded like this. So as long as the two joints are, lying along a straight line, such configurations are all singular configurations. All right. So there are two types of singularity. The first is called.
What is identical?
I'm sorry. What?
What is identical? So two axes of related joints become identical.
Identical in the sense, if the two links are aligned in a straight line, here you can see they are not aligned, right? They are at an angle. There is a relative orientation between the first link and the second link. But here, both of the links are aligned along a straight line. There is no relative, orientation between link 1 and link 2, right? So if the arm is fully extended, it cannot have a velocity. It cannot have a component of velocity along this axis. Or if the arm is aligned along x-axis, it cannot have any further velocity along x-axis because it's fully stretched. It cannot stretch any further than that. So I hope it's clear.
Okay,
Is
sir.
that what you're asking? Is that what you were asking, or?
Yes, sir. Yes, sir. Just I want to know the meaning of identical.
Oh, this one you're talking.
Yes, sir. Above point. Yes.
Okay. Above point, if this would be applicable in case of a robot, uh, which has multiple joints, multiple revolute joints. Maybe I'll give an example. If the first joint is something like this, vertically up, and the second joint is something like this, coming out of plane, and at the end, probably you have a wrist, in all three direction. Maybe, you have a wrist, in this direction, and then you have a wrist in this direction, vertically upward, and also you have, a revolute joint, perpendicular to the plane of the board. So if I consider this to be X, this to be Y, and this to be the Z axis, the first joint is pointing, along the Y axis. The second joint is pointing along Z axis. The third joint is like a wrist, it can rotate in all three directions. You can consider these distances to be zero, right? But for practicality, I have just given some offsets, but in reality, you can consider it to be zero, like a wrist. So the third joint is along X-axis, fourth joint is along Y-axis, and fifth axis is along Z-axis. So it's like an X, Y, Z wrist, like a wrist which can rotate along all three axes, right? So in this configuration, it's all normal, right? This robot can, if you rotate this joint, it can rotate about the Z and X plane. And if you rotate the second joint, it can rotate about XY plane. And, so basically you can achieve all positions, you can achieve positions in X, Y, and Z. And this wrist will give you orientations, X, Y, Z orientations. But what happens if I rotate this joint 90 degrees? If I do that, this entire thing will come vertically upward. So in that case, if I do that, this, maybe I don't know if I can replicate this, if I just cut it and let me see that. If that joint is rotated 90 degrees, it will look something like this, it will go vertically. Maybe I'll change the color as well. Yeah, it'll basically go upward. So in that case, the first joint and one of the joint of the wrist become parallel, right? They become collinear. So if you rotate the first joint and if you rotate the one of the joint of the wrist, it will still give you the same motion, right? Instead of independent motions or independent kind of motion, if you rotate this joint or if you rotate this joint, it will, it won't make any difference. It's still, it'll still give you a same kind of motion. So in a sense, you are losing a degrees of freedom, rather than having X, Y, Z capabilities and, all orientation capabilities, you are losing 1 degrees of freedom because now two joints are doing the same function, right? If you rotate this, the entire robot will rotate about a vertical axis. If you rotate this again, the end effector will rotate about the same axis. It does not make any difference. So like when two revolute joints become parallel or, collinear, that will cause a singularity, that will cause some sort of a singularity. But then it's not a universal case. It depends on the configuration of a robot. It becomes depends on the type of the robot that you're dealing with. So typically we have two types of singularities. Workspace boundary singularities, they will occur when the manipulator is fully stretched or folded on itself. In such cases, the end effector is near its workspace boundary. So in the case we have seen, over here, in case of an RR robot, when it is fully stretched, that means it's at the end of, it has reached its end of the workspace. It cannot move any further than that. So that is a workspace singularity. It occurs at the extremities of the workspace. And the other kind of singularity is the workspace interior singularities. These occurs away from the boundary. In this case, generally 2 or more axes line up. So the case where we have discussed here, when 2 prismatic joint become parallel, or when 2 revolute joint becomes coincident, when 2 revolute joints, basically lie along a straight line, such sort of configuration would lead to a workspace interior singularity, right? They occur inside the working envelope. So, these boundary singularities are easy to deal with because, it occurs at the boundary. So you should plan in a way that your robot will not fully stretch or fully, fold back. But interior singularities are more critical. It can occur within the workspace boundary. So in that regard, you have to do more careful planning so that these sort of interior singularities can be avoided. So these singularities basically occur when your Jacobian matrix becomes singular. That's why we call it as a singularity, right? And Jacobian matrix becomes singular when the constraint equations becomes dependent. And the reason constraint equation become dependent is because because of the joints aligning. When 2 prismatic joints are parallel, it will cause the same motion. Or if 2 revolute joints are collinear, they'll also cause the same motion. So dependence on the constraints will cause the Jacobian matrix to be singular, and that is how you detect singular points. If a Jacobian matrix is near singular, that means the robot is, it's actually near a singularity. So it's better to avoid motions or tasks that is very close to singular configurations. All right. So yeah, that's about the contents. We'll discuss some few 10 sample questions regarding the contents of this lecture. So the first question is, for a non-square matrix with linearly independent columns, the Moore-Penrose inverse can be written as. So it says linearly independent columns. So that means more rows than columns. Right? Your matrix would look something like this. It'll be a very tall matrix, M cross N matrix, where M would be greater than N. Right? Another way to look at this would be, this would be a system of, this would be an overdetermined system of equations. Overdetermined system of equations where number of equations are, more than number of variables. Number of equations are more than number of variables. So if the 3 equations are, if you consider there are 3 equations but only 2 variables, and if the 3, I don't know how to say, if the 3 equations are linearly independent, then there exists no solution. There are no solutions. So in that case, what we do is we try to find an approximate solution such that the least square error between the left-hand side and right-hand side of the equations can be minimized. If our system of equations can be represented as mu dot as j of q multiplied by q dot, we cannot have a q dot that will give you this exact equality. We can only give a q dot which would minimize the least square error between mu dot and the right hand side term. So what would be the pseudo inverse in this case? In this case of an overdetermined system, or in the case when the number of equations are more than the number of variables? Would it be a left inverse or would it be a right inverse? Any answers for this question? Okay, in this case, for linearly independent columns, or when the Jacobian matrix is tall, or when the number of equations is more than the number of unknowns, we go with the left pseudo inverse. Yes, exactly. Left pseudo inverse, which is given by J transpose J, the whole inverse J transpose. This would be the left pseudo inverse. And we have seen how to derive this pseudo inverse expression, at the beginning of this session. So in that regard, the correct answer would be option B. Yes. Now moving on to question 2. For Jacobian matrix with linear independent columns, its pseudo inverse exists if and only if. So it's an extension of the previous problem. So linear independent columns. If this is the case, we would use the left pseudo inverse, which is nothing but J transpose J, the whole inverse J transpose. And for this left pseudo inverse to exist, this should be invertible, right? This matrix J transpose J should be invertible because there is an inverse term over here. So for that pseudo inverse to exist, determinant of J transpose J should not be 0, right? Because we know for any matrix A, its inverse would be nothing but adjoint of A by determinant of A. And this would only exist if determinant of A is not equal to 0. So same logic applies for the determinant of J transpose J to exist. Determinant of J transpose J should not be 0. So in that regard, the correct answer is option A, I believe. If there is any doubt, let me know. I'll just move through the questions. That's indeed the correct answer. Now moving on to question 3. Again, this is like a straightforward question. We have discussed how to propagate velocities, linear velocities. So this is basically the linear velocity propagation. Question asks the formula for linear velocity propagation for a prismatic joint. So how do we do that? The velocity of the next joint, I plus 1, is nothing but the velocity of the previous joint plus the radial component, omega I cross I plus 1 with respect to I. Then we also have the component contributed by the prismatic joint itself. That is nothing but 0, 0, d I plus 1 dot. And since we are interested in a recursive relation, everything will have to be represented with respect to the current frame of reference, that is I plus 1. Everything will have to be represented with respect to I plus 1 frame of reference. And these terms, they are already referred with respect to ith frame. The previous velocity is referred with respect to ith frame. Previous angular velocity is also referred with respect to ith frame. And the position vector from ith frame to I plus 1 frame, which is basically the link length, is expressed with respect to ith frame itself. And in that regard, if you multiply all these equations with respect to the rotation matrix, I I plus 1 with respect to I, all these terms will be represented with respect to the I plus 1 frame. This is already written in terms of I plus 1 frame. I've got a question. We don't have this question in assignment. Okay, so that's the entire point of this session, actually. We are not here to discuss assignment questions, but sample questions for you to solve that will help you to solve assignments. Okay. So in that regard, this is the velocity propagation equation for a prismatic joint. If it was for a revolute joint, this term would not exist. Right? This linear component would only exist for a prismatic joint. And in that regard, I believe the correct answer is option B, this one. Looks to be the more correct answer. Okay, so that's indeed correct answer. Moving on to question 4. The singularity or singular positions of a serial manipulator can be found by solving which of the following options? J is the Jacobian matrix, and for simplicity, it is assumed to be a square matrix. So we know that mu dot is nothing but J of Q multiplied by Q dot. So in the case of an RR robot, maybe theta 1 and theta 2, if you solve, when the two equations, where mu dot corresponds to x dot, y dot, and this q dot corresponds to theta 1 dot and theta 2 dot, and you have this Jacobian matrix. So x dot corresponds to the velocity along x direction, y dot corresponds to the velocity in y direction. And typically, these two equations are linearly independent. But when a singularity occurs, these two equations become dependent. One of the velocities lose its dependence. And if that is the case, this Jacobian matrix becomes singular. It becomes you cannot. It becomes singular because equations are linearly dependent. So to solve for configurations that are singular, or if you want to identify singular configurations, you have to solve the equation determinant of J of Q equal to 0. So solution to this equation will give you the singular configuration. Right? The configurations where singularity occurs. So in that regard, the correct answer is indeed, option B, where determinant of J is 0, or when the Jacobian becomes singular. Right? It's in the name itself, right? When the Jacobian matrix becomes singular, you will end up with a singular configuration. Or at singular configurations, the Jacobian matrix becomes, singular. So that is indeed the correct option. Now, moving on to question 5. For a given RR manipulator, find the linear velocity of the end effector with respect to the base frame. There are two ways of doing it. Either you can use the velocity propagation equation, I plus 1 with respect to I plus 1. This is nothing but Vi plus I omega I cross I plus 1. This whole thing multiplied by I with respect to I plus 1. You can do this starting from I equal to 0, I equal to 1, I equal to 2, and I equal to 3, because there are, you can see how many frames are attached here. If frame 0 is attached to the ground, frame 1 is attached to the first link, frame 2 is attached to the second link, and frame 3 is attached to the third link. So when I is 0, you will get an equation IV1, sorry, 1V1, this is nothing but 1R0 in multiplied by 0V0 plus 0 omega 0 cross 0 T1, right? And similarly, 2V2 would become, 2R1 multiplied by 1V1 plus 1 omega 1 cross 1P2. And all the way up to 3, you can propagate the velocities, and these terms are basically unknown. So you also have propagation equations for angular velocities. I plus 1 omega I plus 1. This is I omega I plus 0, 0 theta I plus 1 dot in case of a revolute joint. And you multiply this with I plus 1 Ri. So you will get this 0 omega, sorry, first equation would be 1 omega 1. This would be 1R0 multiplied by 0 omega 0 plus 0, 0 theta 1 dot. Similarly all the way up to, and once you obtain this 1 omega 1, you can substitute that into here. 1P2 you can know from the DH conventions. And 0 omega 0 is the angular velocity of the ground, that is 0. And 0V0 is the linear velocity of the ground, that is also 0. You can call it as, maybe you can consider it as some initial condition, something similar like that. You can either go this way using velocity propagation, or you already know the forward kinematic equation for a simple RR robot. It typically looks something like X is L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and Y would be L1 sine theta 1 plus L2 sine theta 1 plus theta 2, right? Because this is purely a geometric problem. You can, if the tip of this point is X and Y, the coordinate of this X and Y referred with respect to this theta 1 and theta 2 can be written like so. Okay? And if you take the derivative of this X and Y, you will get the corresponding velocities, right? It will be like X dot would be minus L1 sine theta 1 dot minus L2 cos theta 1 plus theta 2 multiplied by, sorry, it's again sine, multiplied by theta 1 dot plus theta 2 dot. And Y dot would be L1 cos theta 1 dot plus L2 cos theta 1 plus theta 2, theta 1 dot plus theta 2 dot. Right? So if you go with the velocity propagation approach, or if you go by this approach, you will still get the same answer. In case of a simple robot, with fewer joints and fewer links, the geometrical method is always going to be easy. But when the number of links and number of joints grows, you cannot solve it like this. You cannot write this equation intuitively. You will have to use the velocity propagation equations. All right. Okay. So in that case, the answer corresponding to this equations, I believe it is to be option B in that regard. The question only asks you to find out the linear velocity vector. I believe option B is the answer. Yes. Okay, now moving on to question 6. This is an RP manipulator. We have discussed what an RP manipulator is in the previous class. We have a rotary joint like this, and inside the rotary joint there is a prismatic uh, prismatic joint. So the rotary joint is perpendicular to the board, maybe Z1, and this prismatic joint will slide back and forth. So this first link, I'll label this as link 1 and I'll label this as link 2. The first link rotates about z-axis by an angle θ1, and the second link moves to and fro by a linear unit d2, right? So in that case, the question asks, given an RP manipulator, the forward kinematic solution is given as x is d2 cos θ1 and y is d2 sin θ1. Find the Jacobian matrix of the end effector with respect to the base frame, considering only x and y. Right? So if I consider this to be the x-axis and this to be the y-axis and this angle to be the theta, it's fairly straightforward, right? X is d2 cos θ1, y is d2 sin θ1. And how would the Jacobian would look like? Mu dot, which is nothing but x dot and y dot. This would be a Jacobian multiplied by j of q multiplied by q dot, where the components of vector q dot is θ1 dot and d2 dot. And how do you assemble this Jacobian matrix? The Jacobian matrix is nothing but dou x by dou θ1, dou x by dou d2. Then the second row would be dou y by dou θ1. And the next column would be dou y by dou d2. And if you perform the partial derivatives of the corresponding terms, you will end up with it'll be minus d2 sin θ1, then cos θ1, or is it correct? And the second row would be d2 cos θ1, and the next column would be sin θ1. This would be your Jacobian matrix. All right, so what would be the correct answer? I think it is to be option C in that regard. Okay, I hope there is no conflict in that. Okay, now moving on to question 7. Given below is it's not a true or false question. I think there is a mistake over here. I'll just scratch this off. It's a MCQ question. Given below is the schematics of an RR manipulator. Choose the correct condition for singularity when θ1 is pi by 2. So here θ1 is defined as an angle link 1 makes with
Pi by 2.
what? θ2 is?
Pi by 2.
θ2 is pi by 2. Yes, that is correct actually. Because θ1 is, θ1 is basically the angle between x-axis and link 1, and θ2 in this case is the angle between x-axis and link 2. Typically we take θ2 as the angle between link 1 and link 2. Typically this is how we take θ2, but in this case it's the angle between x-axis itself. So in the question, when the robot's first link θ1 is 90 degrees, maybe something like this, This is link 1. For singularity, link 2 should also be 90 degrees, 90 degrees with the x-axis. And for link 2 should also make 90 degrees with respect to x-axis. Because we have already seen that, when the RR manipulator is fully stretched, it encounters a singularity configuration. If you want to prove this analytically, you can, write the forward kinematic equation. X would be L1 cos theta 1 plus L2 cos theta 2. Y would be, L1 sin theta 1 plus L2 sin theta 2. And the Jacobian matrix, as before, it is dou x by dou theta 1, dou x by dou theta 2, dou y by dou theta 1, dou y by dou theta 2. And if you do the partial derivatives of each of these terms, you will get up, you will end up with minus L1 sin theta 1, then minus L2 sin theta 2, then L1 cos theta 1, L2 cos theta 2. This is your Jacobian matrix. And at singular configuration, the determinant of Jacobian becomes 0. So if you consider that, determinant of Jacobian Q, when it becomes 0, you will get, minus L1, L2 sin theta 1, cos theta 2, plus L1, L2 cos theta 1, sin theta 2. This is essentially L1, L2. How would I write it? Sin theta 2 cos theta 1 minus cos theta 2 sin theta 1. I can write this as L1, L2 sin theta 2 minus theta 1. And in the question, theta 1 is already given as pi by 2. And in order for this equation to be 0, theta 2 also has to be pi by 2, right? Theta 2 also has to be pi by 2. Then this becomes 0, sin 0 becomes 0, the determinant becomes 0, right? For a simple manipulator like this, we can obtain the singular configuration just by observation. But for a robotic manipulator with multiple links and multiple joints, we detect singularity by, or we detect singular locations by observing the determinant of the Jacobian matrix, in which locations the determinant vanishes. This is how we do that analysis. So theta 2 as pi by 2 is the correct answer. That is indeed the correct answer. Question 8. It's a true or false question. Workspace interior singularities in an RR manipulator occurs when the manipulator is fully folded back on itself. Is it true or false?
True, no, sir.
Is it true? Or is it false? Because in the previous slide, during summary, we have seen two cases.
True, sir.
Workspace boundary singularities, right? Boundary singularities. And another case is workspace interior singularities. Right? And workspace workspace boundary singularities occur when the robot is at the boundary of the workspace. So for example, if you consider this RR robot, and if you consider, maybe I'll draw somewhere at the center of this page, somewhere around here. So if this is the origin, and if you have an RR robot like this, right, consider it to be fully stretched, at this position. When it is fully stretched, the maximum region it can enclose is this circle, right? So any of these fully stretched configuration can reach up to this circle. It cannot go beyond that circle. So this is one boundary. One continuous boundary is that configuration. And when it is fully folded, right? Fully folded would be like this. When one link goes like this, and the other link comes back, right? So the maximum interior point it can reach would be this inner circle. That is also another boundary. So these are both of these are actually boundary singularities. This is an inner boundary and this is an outer boundary. It can have multiple boundaries. But if both of these links are equal, there is no inner boundary. Inner boundary it can reach all the points inscribed by inside this bigger circle. But if the link lengths are different, there will be an outer boundary and there will be an inner boundary. And boundary singularities occur when the robot tries to reach these positions or these positions. And anything inside, any singularities occurring inside these, within these two boundaries are workspace interior singularities. So the question asks, workspace interior singularities in an RR manipulator occurs when the manipulator is fully folded back on itself. So that is false. That's false actually, because when the manipulator is fully folded back itself, it goes to an inner boundary. This is a boundary. This is again another boundary. This is still a boundary. This is when the robot is fully extended. And this is when the robot is fully folded. I hope that is clear.
Yes, yes.
Right? So anything in between, the robot's workspace is only this region, between these two boundaries. So this region is considered as a boundary. This region is also considered as a boundary. So this boundary occurs when the robot is fully extended. This boundary occurs when the robot is fully contracted. And any singularities occurring within this boundary is interior singularity. So the question, it's not correct actually. It's actually false. Right? Interior singularities occurs, when two prismatic joints are parallel or two revolute joints are coincident. And when the robot is fully folded, that means it has reached a boundary. When it is fully extended, that also means it has reached a boundary. So, the statement from here to here applies only to a boundary singularity, not interior singularities. Okay, so I hope that is clear. It's actually false. Workspace interior singularities generally occur when two or more axes line up. Such scenario never happens in an RR manipulator. Again, in case of an RR manipulator, we don't have interior singularities. We only have boundary singularities. Moving on to question 9. I think we have already solved this, right? Linear velocity propagation equation. I think we have solved a similar question actually earlier. So I thought B was the answer. Yeah, I think we have solved it previously. Yeah, I think, sorry for that. I think it's a repeat question. Moving on to the final question. For a manipulator, a Jacobian matrix is given as so. If the end effector force is given as this vector F, what will be the joint space input vector tau? So just like in kinematics, we also have seen a mapping between joint space, wrench, a combination of forces and torque. I'll use it. I'll use the letter tau to represent the joint space wrench, and the wrench at the task space or at the end effector, I'll denote it as with a capital F. And how do we map this wrenches in joint space and task space? We have already derived this expression using the conservation of power. The correct expression is tau would be J transpose F. So in the question, you have been given J, you have been given F. So it's only a matter of taking J transpose and F. So J transpose from the question would be 101, 1 minus 10, 0, 10. And if you multiply this with F, 201, you will get 2, 1, and 2. So I think option B is the correct answer. Yeah, that is indeed the correct answer. Yeah, so that's it for today's session. All the questions for the assignments are more or less similar. Instead of velocity propagation of prismatic joint, you will be asked, propagation equations for rotary joints. So, questions will be of similar complexity. Whatever we have discussed, you can expect, similar questions of similar pattern. So if there are any doubts, I can clarify it now. Otherwise, we can wrap up this meeting. How to find Jacobian if x and y are given? All right. So typically, if you have, x as a function of joint variables f1 of q and y a joint variable as, maybe I'll, write it as a function of two joint variables, theta1 and theta2, and y is another function of the same pair of joint variables. If you're given x and y, x dot would be dou f1 by dou theta1 multiplied by dou theta1 by dou t. This is nothing but dx by dt, right? We are simply applying the chain rule. Plus dou f1 by dou theta2 multiplied by dou theta2 by dou t. And similarly for y, dy by dt would be dou f2 by dou theta1 multiplied by dou theta1 by dou t plus dou f2 by dou theta2 multiplied by dou theta2 by dou t. And this will be your x dot y dot vector. And if you group the right hand side into a matrix vector format, you will end up with dou f1 by dou theta1, dou f1 by dou theta2, dou f2 by dou theta1, dou f2 by dou theta2, and this vector would be dou theta1 by dou t. Now that is nothing but theta1 dot, and this would be theta2 dot. So this term would correspond to your Jacobian, right? If you are given x and y as a function of joint variables, if you, take the partial derivatives of the functions with respect to joint variables and assemble it in this manner, you will get the Jacobian. I hope that is clear. Okay, any further questions? Okay, if there are no more questions, we can log out. Thanks all for joining.
Thank you very much.
Thank you.
Thank you, sir.
Thank you. Okay.